Today, I'm going to show you how to make beautiful, professional plots in the main plotting library of Python, Matplotlib. We'll start with basic line plots, eventually getting to things like histograms, 2D color plots, contour plots, and at the very end, we'll look at animations. My goal here obviously isn't to show all the features of Matplotlib because there's so many, but more so to go through my workflow in Matplotlib, how I approach making a plot, the steps in coding that I take in order to make a plot look better and better and better, and even the little techniques that I use in the process. Please remember to like and subscribe. Come join the Discord server if you want to talk with other people in physics and math that share similar passions. And let's get started. So since this is a Matplotlib tutorial, I'm only going to be importing Matplotlib and numpy, and we'll keep all the sort of physicsy, sciencey stuff to as simple as possible in this video. Now, Matplotlib on its own doesn't actually make that nice of looking plots. And so if you want to get a nicer format here, I would recommend installing Streamplots. And it just gives in some additional plugins for Matplotlib. So for example, if I import these packages here, and it allows me to use this plot.style.use. You know that I've imported Matplotlib pyplot as PLT. And I can specify some options. So I think the best options are science, notebook, and grid, like this. So this just makes the figures look nicer. And so we'll start with some quick plotting here. So if you want to do a simple line plot, right? Suppose I have some x data here. X goes from 0 to 15, right? And y is equal to sine x plus a little bit of noise. And we want to make a quick plot here. The simplest way to do this is just plot.plot xy. Of course, this plot doesn't look great. There's more features we can add, but I'll show you what it looks like if I don't have science plots here. So if I set it back to the default, right, this would be switching everything now. So this is default. Then the plot looks like this. And I think this looks gross. This looks like someone took a crayon and scribbled on paper or something. It's not for me. So I use the science plots, and this is like professional paper type plots. And so you get something that looks like this, but of course it has no labels. It's shaped kind of like a square, and there's a lot of features that need to be customized here. In addition, this is a bunch of points, but it's drawing lines between them. So the first thing we might want to do is change how the line is actually drawn itself. And so I can change the way the line is drawn. For example, if I give this option, just this quotation, this is the third argument here, it draws it as a line as is. If I go dash dash, it draws it as a dash line. If I go O dot dash dash like this, then it'll put a point at all the actual data points, because what Matplotlib does by default is it plots all the data points and then it connects them by these linear interpolated lines here. And so if I actually want to see my data and then the interpolated lines, I can go like this, right? And you see that the data is actually only at these blue dots here. Now, if I didn't do the dot dot and just plotted the data, it looks a little bit messy. So this is where you kind of have to be artistic, right? You want to show a relationship or something that's happening in time. If I showed you this, you know, you might not get a good idea of what's happening. But drawing these interpolated lines, I like to do it as dashes because this, of course, isn't actually real data. This is just showing an interpolation. Then this gives more of a structure to someone when they're looking at it, sort of like an object that you would see in real life. Of course, I can also change the color too. That's the other thing about the line. I can go color is equal to purple. Red, blue, all the different colors work, of course. I can change the line width. So for example, line width equals 0.1. That'll make the dash line really small. You can play around with this, right? You notice what I'm doing? I'm sort of rerunning the code over and over, and this is typically what I do when I make plots, right? And you can find a line width that sort of works. So for example, maybe I would want 0.7. So you see it, but it's not overwhelming on the plot. I can also change the point size too. MS is for marker size. I can make it really big, but then it looks kind of gross. I can make it small, but then you can't see the points. So you have to play around with these parameters until you find something that sort of works for your particular plot. And it involves basically rerunning the code over and over. So now you know if you have some data, some sort of X versus Y data, you can do most things like this, right? This is for the line itself. Of course, something else you might want to do is change the figure size. Maybe you don't like this box here. You want it to look a bit different. So to do that, you had a line before this, and I would go plot.figure, if I can spell, and I give the argument fig size is equal to, say 8 by 3. I like that size. So that's 8 in X and 3 in Y. So that gives like an aspect ratio here. And I can do that plot, and it looks a little bit, maybe this is something you're going for in your plot, but it gives it a different aspect ratio. And you can play around with this, right, until you find a shape that sort of works for you, for your particular plot. And I should put that here under where it says figure size. Now, of course, the next thing you want to do that, of course, you'll be docked marks for in any course if you don't do this, and you'll be flat out rejected if you try to submit this to any journal, is axis labels. So I can go plot.xlabel, and suppose I want to say like, this is voltage, and this is measured in V for volts. And I can go plot.ylabel. First of all, this will be voltage. The x-axis will be time in seconds. So maybe you're measuring some voltage as a function of time here. So that's sort of typical what you might see. You can add a legend to the plot as well. Now, a legend is usually if you have multiple things plotted on the same plot. But, you know, for example, notice how I'm adding things more and more to the plot. But if I go plot.legend, and suppose I labeled this, so I give an additional argument here to this plot, label is equal to, maybe it's component 1 of my system, then it'll draw a legend here. And I can change the location of that. I can say, for example, loc equals upper right, and it'll put it in the upper right-hand corner, and I can put it wherever I want on this plot. And so if I had 2 lines here, I could distinguish between which is which with a legend. And I can change the font size of that legend too. For example, font size is equal to 10. Maybe the legend's too big, and I get something that sort of looks like that. So like I said, it's easy to have multiple lines on the same plot. And so maybe this is data that you measure in the true lab, and you want to plot it next to a true sine curve to see what it looks like, right? And so this is data, and you have this true sine curve here given by a function, sine of x. And so here I won't want to draw individual points. I want to have a smoother looking green curve to plot over top. And so you'll note that that'll show up in my plotting style, right? So here with the first component, I use this particular style. The second component where I'm looking at x2 and y2, I'm not going to use O dot dot because I don't want to put an O at the points. I'm also not going to use a dash line here. I'm going to use a single line, and notice that I have more points. 100 points between 0 and 15 is very dense. I might change this color to green, and then I'll call this component 2, for example. And if I plot this, you can see I have my sine curve next to this. Now, maybe I don't like the dash line anymore, so I can get rid of this. And I have the points, and then I have my curve. So this is like how the data is sort of looks like compared to reality, which is this sine curve here. And maybe you do a best fit and obtain this sine curve from this data. So you can see already that there's quite a bit going on here. Now, you'll note that the legend is kind of taking up some of the plot, and there's many ways to deal with this. One way is by adjusting the x and y limits. So maybe I still want this in the upper right-hand corner, but I need more space. So I can go like this, and if I adjust the y limit, plot.ylim, right? And there's top and there's bottom. So I can say top is equal to, right now it's about 1.1, but say I set it equal to about 1.5. And it still doesn't have enough room for the legend, but you notice that there's more room here than there is here. The other thing I could do is I can make the legend 2 columns. So for that, I would use the ncol argument. Ncol is equal to 2. And you'll note in this tutorial, I'm sort of spitting out a lot of things really fast. What I recommend is if you really want to learn Matplotlib well, then every little thing I'm mentioning, like, making the legend like this, or like changing the y limits, just write down these individual notes because you'll never know when you'll need them, right? And so this makes it a little bit easier. And so instead of component 1, component 2, I'd probably label this data and theory, for example. Because now my data are these points, and my theory is that it should be a true sine curve, for example. Something that I deal a lot with in my research is histograms. And so these are really important. So here I just have a bunch of numbers, right? It's just a list of numbers. And suppose I want to make a histogram of these values. Well, a quick histogram is just plot.hist res. And you'll see it returns 2 objects here. It actually returns the edges of the bins. So this would be like, so the edges of the bins are here. And then the counts in each bin. So that says there's 2 between these 2 values, 15 between these 2 values, etc., etc. So if I say like a is equal to plot.hist, I can actually extract a as 2 numpy arrays here. If I wanted, for example, to get the bin edges and the number of things in each bin. That's a little trick for Matplotlib. Now, maybe I don't want this many bins, right? This is the default number of bins. Well, I can set bins is equal to 100, for example. And I don't want to set it equal to A, but I'll just go plot.show. And you'll see now there's 100 bins, but maybe the histogram's a little bit too sparse. I have too many bins, right? So if I make the histogram too dense, there's too many bins here, then there's not enough things to fill each bin. So maybe here I want 30 bins, for example. I can get a decently good-looking histogram. And I'd also probably want to change the figure size here. I like that 8:3 ratio. So now I get a histogram that kind of looks like that. But shows the number of entries on the y-axis. Maybe I want a normalized histogram, which means that the area under this is equal to 1. Well, from that I could choose the argument density is equal to true. And now it'll plot a density such that the area of this thing is equal to 1. So this is now a density plot as opposed to a histogram. And this is more popular because suppose you collect data and you collect 10,000 things one time, you collect 30,000 another time, and you plot two histograms over top of each other. You want to compare them even though you don't have the same number of data points. So I prefer density plots a lot of the times. Yeah, so this is what I did here. So I'm just going to get rid of this. And I can also use a different style of bins. Now, sometimes you want to put two histograms on the same plot. And that's kind of annoying when they take up space like this, because maybe I have another one that's a little bit wider. And if I plot them over each other, then one's going to be covering the other one. This shows up a lot in my research. So maybe I have these other residuals here as well. Or they're just an array of values. Well, if I go like this, for example, if I just plot them over top of each other, like this, you'll see that they cover each other and you can't actually extract what you want from here. No one knows what's going on with the blue. But what I can do is I can go hist type is equal to step. And you'll see what this does. And this is my favorite argument for histograms here. And now you can see that it only draws the top of the bars, and this makes it very easy to compare histograms on the same plot, for example. So very useful to keep track of that as well. Now, so far, I've only used a very basic API in Matplotlib, but typically sometimes you're dealing with multiple plots on the same figure, for example. I call them individual axes, and then you have a figure that contains many of those. And maybe you want to add text to plots. That's kind of tough with the basic API if it's complicated. And then creating animations, you also need to use this more advanced API. And you can do more with it, but it just requires a little bit more coding. And it requires defining things a different way. So for example, you would have to use fig ax is equal to plot dot. I always use plot.subplots. One row by one column. So you see what I'm doing is you create an array of plots on the same plot, but I make it one by one, so it's just one single plot fig size. And you'll see that come up more later in the tutorial. And I'm going to make the fig size 12 by 4. And it creates a figure, and there's one ax called ax on this figure. And so I could make it 1 by 2, for example, and then I have two plots. You notice that one row by two columns. That's what's going on. That's what you see here. But right now I just want 1 by 1. So this creates my figure. And then I do all the same commands as before. Ax.plot, x by, and then o dot dot. Everything looks very similar to before. And instead of x label and y label, it's actually set underscore x label. So normally you have plot.x label and plot.y label. Here it's ax.set x label. So I can set whatever. I'm not super interested in, whatever, but you can set your x and y labels like this and do all the same thing that we did before. And plot.show will show it, right? So this is like a slightly different API, but you'll see later that this comes in handy, especially like I said here, multiple axes in one figure. So, suppose I want to do this, and maybe I want 3 rows by 2 columns plot. I need to make sure that the figure size is appropriate for this. So 12 by 4, right? If I have 3 rows by 2 columns, this isn't going to work. So maybe I want 12 by 12 here. And so now my axis, if I just look at this, if I look at axes here, I actually have a 2D array of axes, and each one contains a separate axis. So I need to index them appropriately, right? So I can go like this, and you know, suppose I want to select one, right? Well, I would go like this. This is how I do it, the workflow that I sort of use here. So I'd go axis equals axes 0, 0. So 0, 0 means take the top left one. 0, 1 means take this one. 1, 0 is this one. 1, 1 is this one. So 0, 0 is the top left. And then I would do everything I need to do to the first axis in a couple lines of code. And if I want to do something to another axis, right? So then maybe I want to make a histogram at 1, 1, for example. So that would be this plot here. I could go ax.hist, and it's just all the same arguments that I'd have here, right? So suppose I do this, ax.hist, all this stuff here, and it sets x labels and y labels, and you see that I have my thing show up here. Like before, I can add anything, multiple things to each plot here, like I did before, and I can add legends to each axis. I can do all that. For example, if I label this, label equals, you know, component 1, I'll just call it comp1. And then I can call, for example, ax.legend here, and it will give a legend in this particular axis of the figure. So it's very easy to generalize this sort of thing and have code run like this. So this is multiple axes in one figure. You can also set titles to each axis. So ax.title histogram, right? This is my plot that has my histogram. And you have to use set title for axes, not just ax.title. And so I could label each one of these appropriately as I see fit. Another thing that's really common is you might want to add text to part of a plot here. And so for that, for example, suppose I want to add text to this axis. Well, I'll make sure I'm in this code here. So ax.text. And 0.1, comma 0.1, that'll go here. And then this is x. So as this gets larger, it goes to this side of the plot. And as this second argument gets larger, it goes up like this. So that's how you label that. So 0.1, 0.1 is near here. I would normally experiment with some values until I find something that looks nice. And I could just call like text. That's the or text here, for example, the string that I want to put. And, you know, if I just put 0.1, 0.1, it will go to 0.1 here. It'll take the literal values here from the plot. But I like using sort of a dimensionless way so that 0.1 or 0, 0 corresponds to here and 1, 1 corresponds to here. So you can do it regardless of the dimensions of your data. And for that, I call transform equals ax.trans axes. And so this is just an additional argument you need to add if you want 0, 0 to correspond here and 1, 1 to correspond here. And I can add text, and you'll see that the text shows up here. And I'll get into that a little bit more later as well. There are other things too, right? I'm going to keep adding things in this tutorial for things to know. Maybe you don't like these numbers, they're too big. Maybe I want to make them smaller. Well, I can go like this, ax.tick_params. And I would say axis equals both. I want both the x and y axis of this plot. And I want to say which is equal to, well, don't worry about this argument, I guess. And label size is equal to 10. So it sets my font size here equal to 10. So now on this plot, you'll see that the numbers are a little bit smaller. And then maybe you want to do that for all axes as well to make it look a little bit nicer. So again, these are all sorts of things that you can play with, and I'm just sort of handing things out here. Again, take notes on this, it'll come in handy, and this stuff will show up. So as an example, I'm going to create a plot that I think is sort of what I would call a professional plot for like something I would put on my thesis, for example, or something you might see in a paper. And it requires putting a lot of data on one plot here. So I have these 4 arrays, res A1, res A2, res A3, res A4, or A2 and B2. And they're just sort of things that I'm going to make a histogram of. And so A1 corresponds to one thing and B1 corresponds to another. So suppose I'm collecting data for 2 different processes, A and B. And so this is trial 1 and this is trial 2. And I want to put trial 1 on one histogram. Then maybe I fix my equipment, I do it again. And I have the second trial with the new data. And so I have 4 arrays here. And for example, if I'm doing stuff really quick, I could go plot.hist res A1 with 100 bins. And make sure I have plot.show as well. And for example, this is very quick of what you might see with the data. But you can see 100 bins is obviously too much. And this is not a great looking figure size. There's some text I'm going to add. I'm going to add the standard deviation of these, right? Because these are histograms, which means they have a width to them. and I'm going to add the standard deviation of these. So for example, I have these two text strings here, and all it is it's LaTeX code with, this is /n means new line. So this is on one line, it's going to print sigma a is equal to, and this is using f strings of Python, is equal to the standard deviation of res1 with 4 decimal places. And then sigma b for trial 1 is equal to the standard deviation of this. I do it for text string 2 as well. This makes it easy to add this text to the plot, so I do this beforehand. Now for making the plot. So fig axis is equal to plot.subplots. I'm going to make one row by 2 columns. Remember, 2 columns, so the plots are going to be like this. This is for trial 1. Then maybe you're experimenting, you fix your equipment, you collect these 2 arrays, and I'm going to put these on the other plot as well. For a good fig size I found here, it was about 10 by 3.5. So for example, this is what I'm creating, and I'm going to put trial 1, my first data here, and my second run of this data here for process A and process B. So it's kind of abstract, but whatever. Then the first thing I do is I want to deal with this axis. So I go x is equal to axis 0. So that takes the first one here. You'll note that here I had it indexed as axis 0, 0 because it was 2D. Here, because it's a 1D, I can just index the first element and it's just a one-dimensional array. Then I can start plotting things. So ax.hist res a1. And I get something like this. And I'm going to add plot.show at the end. Plot.show basically gets rid of all this stuff here. Oh, when I do this. So, okay, it's not exactly what I want. Maybe I want 30 bins. And I want to make it a density plot, like I said, when you're comparing data together. And his type is equal to step. And so this looks good. And now I can plot the other thing on this plot as well. Res B1. So I have 2 things on the same axis. I also want to label this. So this is label is equal to process. I'll just call it A. And this is B. And I want to add a legend, ax.legend. And I'm going to add it to the upper right. So I need to call loc is equal to upper right. And now it adds a legend here. So I know which is process A and which is process B here. Some other things, I want to add the text here from this. So I can go ax.text. I found a good location with 0.05. So that's like right near here, and 0.81, which brings you up here. 0.81, and I'm just going to add text string 1, and I have to add transform equals ax.trans axis like this. So now I have this up here, but you'll note that there's these grid lines and it doesn't look that great, and so I'm going to add a white box around them, and for that I need to call bbox is equal to dictionary, and now I pass in some arguments. Face color is equal to white, and edge color is equal to black. So Matplotlib sometimes works in these weird ways where it passes arguments, but this is basically passing an additional thing called bbox, and with specifying the face color and the edge color in a dictionary. And so now I have this nice box around here. And for the legend, I don't want this fancy box. I also want this to be a little bit more square. So for this, I call fancy box is equal to false. And you'll note, again, there's all these weird arguments in Matplotlib. I also want the edge color to equal black. So now it matches this. So now this is starting to look a little bit nicer, right? And I can set my y label, for example, ax.set y label. I'm going to call this density, and well, because these are the same units, I'm actually going to use a fig subtitle here. So fig.subtitle. This is if you want to add a label to a figure, right? I can add labels to the individual axes. I can also add a general figure subtitle here. So I want to add it down here. And not subtitle, I want to add text. So I'm going to add it at 0.5, so it's in the middle in X. Negative 0.04, so it's slightly outside of the plots, of course. And I'm going to call it, maybe I'm measuring delta E. So change in energy of some sort of process, you know, something abstract. And it will add this in the middle. I want to make sure it's centered. So I call, where's this here? See, sometimes the arguments are not so easy to remember. Horizontal alignment, HA is equal to center. And now I have this in the middle, and maybe I want the font size equals 20. So it shows up. So now this sort of applies to both things here. And it's measured in joules, for example. So I can say joules. And now I have this X label that applies to both these here. And basically, I do the same thing as I did for this axis for this other axis. Only this time I'm plotting A2 and B2. And I'm adding text string 2 here that corresponds to the, where is this? Text, yeah, text string 2, which corresponds to the standard deviations of the second process. And I need to make sure this is axis 1. And now I have this here and this here. And maybe I don't like green and blue, right? Well, I can label this color is equal to blue. I actually don't like the default colors very much. I prefer these colors here, so blue and red. And note that this has a little bit of a stronger look to it. This is more, in my opinion, it's more professional. Maybe some people don't prefer it, but I like my plots to look thick, you know, have nice colors like this. And maybe I don't want a legend on the second one, right? Maybe you don't want the legend here, so I can get rid of the legend on the first axis. Again, the important thing here is not only learning the code, but the sort of thought process. You can see what I'm thinking as I make this. And I don't want this repeated, right? I want a Y label that sort of corresponds to both plots, because this looks kind of ugly. So I can also get rid of the Y label from this plot. And now I have a nice looking plot, right? And maybe I want to give a title to each axis. That's an option too. I can go ax.set title. This is trial 1. And I can do that to the other axis as well. Trial 2. And this, in my opinion, is a very nice looking plot, right? You have the standard deviation for both trials. You have a legend here that tells you which is trial A and which is trial B. If I was going a little bit more advanced, I might somehow color this, but then sometimes that doesn't look very nice either. But this is a really nice plot here of plotting histograms on the same plot. Of course, something you also deal with all the time is if you have something that's a function of 2 variables, for example, z that's a function of x and y, you can no longer plot it as x versus y. You need 2-dimensional plots. And maybe 2D is the wrong term here, but what I mean is 2 independent variable plots. So for example, here I'm creating an array z that's a function of x and y. So x, y, and then z is some surface. How would I plot that, right? And there's many ways to do this. And this sort of data comes up all the time. And you could make a 3D surface plot, and I'll show you how to do that. But it's typically not the ideal way to deal with this sorts of problems. One way is filled in contour plots. This is sort of like a color plot per se. So I can go plot.contour f. This f is for filled in. And I just give x, y, z. And it'll make a contour plot like this. And so wherever you see the same color, this is sort of the same value. Now, obviously, it's not discrete like this. Like, this isn't all the same value. That's because there's a specified number of levels. And I can change that. Levels is equal to 30, for example. Now you have more of these contours, right? That's what a contour is. It's a line of a constant value. And now you can see that the function gets higher here and lower here. But what do the colors actually correspond to, right? And for that, you probably need a color bar. And so now I have a color bar on the side that tells me the value corresponding to what color, right? And I can set labels for my color bars, right? Label, I think you do it like this. And I've got ASD showing up here. So I can put a quantity here. Maybe I'm measuring like the voltage in space. Like I have a table and there's, you know, some sort of configuration here. And maybe the voltage is high here and here. And then I would label this voltage, for example. You can make them more dense by changing the levels, as I've said. You can use Vmin and Vmax to adjust the color range. So for example, maybe I want everything under 0.72 to be the darkest color. Well, then I would go, I would add this here, Vmin equals 0.7, right? And now everything that's 0.7 or less is going to be the darkest color. So that's the minimum value. I could do the same thing with the maximum. Maybe I want everything over 1.68 to be the brightest color. So then I would go Vmax is equal to 1.68. And now everything that's greater than 1.68 is this yellow color. And now it isn't really useful for this example, but you know, suppose you're plotting a 1 over x function or something that diverges. A function that gets really, really big. Maybe it's like in this range and then all of a sudden shoots off to infinity. That can be really useful so that it keeps the color range in the area that you're interested in. For example, if it suddenly started increasing rapidly here and went up to 20, then I might want to set it only in a small region, right? Then I might want to set the max equal to 1.92. So again, things to consider when you're dealing with these plots. Maybe also you don't like this color map as well. And so I can change the CMap argument. CMap is plasma, for example. That's a different color map. And it changes it here. And if you want to look at all the different color maps in Matplotlib, I think they have them all right here. So if I click on this, it would bring me to all the various color maps, the options here. And so you just give this number as a string, and it will use this as your color map, for example. Now, sometimes you actually want a pure contour plot, which is actually literal lines, like you might see on a map, for example, lines of constant altitude. And that's preferable in some cases. And so you could go plot.contour x, y, z, and it actually plots these lines of constant value. And now this doesn't look really good because you don't know what value these are. The colors are kind of weird. And this is the way that I like contour plots the best. So first of all, I save this as an option, as an object. That's, it keeps this information here. Then I can add these color labels to this plot. So I could go call plot.cLabel. And then I pass in CS, so it has access to this information. And watch what this does. I can get font size is equal to 8. And it actually will write in the value of each contour here. And so this is really useful because rather than having to look at some color legend or whatever, you can see the values specifically here. And if you don't like the number of lines, if you want there to be more lines, you can add more, same as before, levels equals 20, for example. And you get something that looks a little bit more dense. And I like this, right? This is a really nice looking plot. You have a combination of the colors, which sort of guides your eye to making it look like it's larger, but then you can also see the specific values themselves. So contour plots, even in courses like E&M and stuff, when you're plotting potential, lines of constant potential are an important concept in E&M. And so this sort of plot is useful. Finally, you could create a 3D surface plot directly, and this isn't a great option, I would say, and I'll show you why. So fig axis plot.subplots, and here I need to add a certain keyword argument, subplot underscore keyword argument is equal to a dictionary like before, and notice how this comes up in Matplotlib. Projection is 3D, and there's something wrong here, and that is because I'll just give it like this. That's how I'm used to doing dictionaries, curly braces. And now it creates this 3D plot like this. And I can plot the surface as follows. Ax.plot surface x, y, z. And I'm going to use a cool, warm color map. So that's one of the options here. And you see that you actually have this surface plot here. Now, the problem with surface plots, if you put them in a paper or something, is, we have the color here to at least tell us which part is higher, but it's not really obvious what this looks like, right? Unless you had like a full sort of 3D objective view, this isn't that nice. Now, I'll show you in a bit how to make an animated GIF of this where it rotates around. And then, in my opinion, in that case, this is a much more preferable plot. But just like this, it's not a very nice looking plot. Streamplots are really useful for plotting vector fields. So here I have some X and Y data. That's just a mesh grid, right? And U and V are specify the X and Y component of my vector field. So at every point in space, there's a vector. And this speed here is the magnitude of the vector. So I also keep track of how big the vector field is there. So maybe you have wind. It's really windy at some parts pointing in one direction. It's not very windy in other parts pointing in another direction. And that's contained by U and V. So I'm going to make a 4x4 plot here showing all the different options you can do for this. So fig axes is equal to plot.subplots. I'm going to make it 2x2 and fig size is 5x5. So I'm going to do a different thing in every one of these little axes here. I'm going to make it actually 7x7. So the first thing I'll do is I'll start with my first axis. And I'm just going to use the regular stream plot. So ax.streamplot. It has to take in my X and Y mesh grids. and also my u and v components. And it will just make a stream plot here, right? This is kind of nice because it tells me which direction the flow is, right? So it's almost like if this were a water stream, this is the direction that it would flow. But it doesn't really give you a sense of the magnitude of these vectors. For example, you don't know if it's flowing faster here or faster here. And so in order to find that out, I can go a different plot, and I can actually change the speed based on the color. String here, color equals speed, because I've defined the speed here. And so it uses the regular thing, so it means that whenever it's yellow, it's going faster, and purple is slower. But in my opinion, this still doesn't look great, and there's actually a way that I think is the best to do this. So I'm going to make it on this bottom plot here, 1, 0. And I'm going to define this thing called the line width. So I'm going to change the line width based on the speed. And I think this is sort of a more artistic way to do this that looks better. So I'm going to change it to 5 times speed. It's going to be proportional to the speed, divided by speed.max. So the largest line width is equal to 5. Or sorry, the largest line width is equal to 1, and then it gets less than 1. And so here I go, line width is equal to, or line width, that's the argument, is equal to LW. And now on this plot, you see that these larger line widths are where it is faster. So you can see there's not much flow in the center, and it gets faster moving outward. I think this is preferable to this plot here. And you can also look at lines of constant flow. For example, if I start at a particular point and I'm in the water, for example, how am I going to move? Well, that's what I'll show in my final plot here. So I like this line width here feature, but maybe I don't want it for the line of constant flow. And so I can make start point is equal to, and I'm going to make these seed points. So seed points, this is the example of some starting points. And it's an NP array. And my first starting point is going to be at 0, 1. And my second point will be at 1, 0. So this is x, y. So x is 0, y equals 1. And x equals 1 and y equals 0. So I'll start here, and it will plot the lines of the direction of which I'm going to flow. So my seed points here are x equals 0, y equals 1. That's going to be my first starting point somewhere here. And my second is x equals 1, y equals 0. So start here. And I want to look at the lines that the flow that I'm going to do. So only those particular lines. And so I can plot that like this. And you see that this is the 1, 0 point. So this is the flow line corresponding to that point, and this is the flow line corresponding to the other point. So another feature of these vector plots that I think is pretty cool. Image reading is really easy using Matplotlib, and they have a function to actually open PNG images. So here I have an image of a flower saved as a PNG, and I open it, and it automatically will open the pixels into a numpy array. And if I want to plot the image, plot.im show im, and it will plot that image on a plot here. So again, really simple, and I don't want to get too much into this, but image reading is very another thing that you could look into in Matplotlib for sure. So the last thing I want to look at is animations, or making animated GIFs in Matplotlib, because I do this in a lot of my videos, and I think it's a really cool feature of Matplotlib. So for example, this function here, f of xt, is a sine wave, x minus 3t, that moves at 3 meters per second. So I can plot at any point in time, any given t, I can plot the sine curve. The question is, t increments, the sine curve sort of moves to the right here, right? So it's moving over as a function of time. As time gets larger and larger and larger, the sine curve will shift on the plot. And so can I actually make an animation of the sine curve moving over? Well, I can, and so let's start sort of basic here. So I can plot x and f of x 0, right? And the sine curve looks like this. Now over top of it, I could also plot 0.1, right? So here time is incremented a little, and it's moving over to the right a little bit. And of course, as time increments more, 1, it moves over here to the right. And 1.3, for example, it's sort of moving over more and more and more. And I want to make an animation of this blue curve here just moving over on a plot. And so I can do that pretty easily. So I need to import the animation libraries, animation and pillow writer. And this is how you do this. So it's pretty similar for every time you want to make an animation. It's always sort of the same thing. So I need to use this API, the figax1, plot.subplots, 1 by 1, and fig size. I'll make it 8 by 4. I think that's a good figure size. So this is the axis of which I'm going to make the animation on. Before I make the animation, I want to store this empty line data and empty time data. So I'm going to display the time, and I'm also going to plot the thing, but I want to make those objects but not initialize them with anything yet. And so, for example, I can go line 1 is equal to plot.plot, and it's just going to be empty, right? So I'm plotting an empty line here, so nothing shows up. Same thing with this text. So I'm going to call this time text is equal to ax.text. I'm going to put it at 0.65, 0.65, 0.95, and no text, right? So it's empty right now, and font size is equal to 15. And I'm also going to use transform. I'm just going to copy from what I had before. See, I'm lazy. It's not good to type this all out every time. Yeah, this is what I want. So now I have all this stuff that I want. So it creates an empty time text with nothing in it so far and an empty line. And we're going to add to these lines and change them in an animation. And so for this, you need to define an animation function. First, I'm actually going to set the xlim and ylim 0 to 10 times np.pi. And x.set ylim set it minus 1.5 to 1.5. Otherwise, it will keep those initial limits. And so this is the sort of limit I'm looking at here, which translates to, right, I'm plotting from 0 to 10 pi here. So that sort of translates to our problem. And so now we need, at each frame of the animation, we need to update it. And for that, I need an animation function, which you call def animate. And all it takes in is the frame number, I. And so we need to change the animation as a function of the frame number. And so here I'd go line1.set data. And I'm going to set it to x and f of x. And now I need to have some time at t, right, related to the frame number. So if I go 1 over 30 times I, right, then the time is 1/30th the frame number. So this is something you sort of have to think about. But if I'm making an animation at 30 frames per second, which I'll show you how to do later, 1/30th times I means that every second, or every 30 frames, they're equivalent, right? 30 frames per second is 30 frames in a given second. I'm going to increment t by 1. So that's how you relate this, right? The frame number. You have to think about what you're doing here. If I was going 50 frames per second, which I'm actually going to do because 50 frames looks nicer, then every 50 frames, or every 1 second, t goes up 1, right? So at the 50th frame, or after 1 second, this is going to equal to 1. After the 100th frame, or 2 seconds, this is going to equal to 2. So you have to adjust this appropriately. And I'm also going to time text. So these objects are initialized up here, but I changed them here. Dot set text. And I'm just going to go t is equal to 2 decimal places, dot format. And the time is going to be I divided by 50. So this is the time that's going on here. And now to animate, I go any is equal to animation dot func animation. I pass in my figure. I pass in the animate function that I've defined personally. I'm going to go for 240 frames. Interval doesn't really matter for what we're going to be doing. Interval equals 50. And so this sort of creates the animation, but then I need to save it as a GIF to my computer. And that's where you specify the frames per second. So I go any.save. I'm going to save it into this folder, images/any.gif. The writer I'm going to use is pillow. And I want to save it at 50 frames per second, right? That's why I put this 1/50th here. So FPS is equal to 50. And the resolution, DPI, is equal to 100. And so then I can create this animation here. Okay, so the animation has been created. You can see it's a GIF, and the time increments from 0 to 4, and my curve is moving over to the right just like I want it to. So very easy to make an animation in Matplotlib. Now, you'll recall earlier that I had this surface plot that I said didn't really look that great, but we can make an animated GIF of it rotating to make it look a bit better. And so it's the same sort of procedure that you do up here. So I'll copy and paste this code. This is the surface, of course. And so I just need to change a few things to make it work well. So instead of having this line 1 in text here, I just go ax.plot surface. Also, I'm going to use the default Matplotlib here. I know I said it looked ugly, but default. I think it looks better than this one for the surface plots. So, you know, sometimes it's better. And I'm going to use cmap is equal to cool warm. Line width is equal to 0. Anti-alias is equal to false. These are just some arguments that I add here. And my initial viewing angle, I specify the azimuthal and elevation. So my elevation is going to be 10 degrees. My azimuthal angle is going to be 0 degrees. And now I want to make an animation, and I want it to be a GIF such that it rotates, and at the end, it gets back to its initial position, and then it rotates sort of continuously, right? And so I can put that in appropriately with the animate function. So here I just go change the viewing angle. That's all I really need to do. So I go ax.viewInit, and I'm going to make the azimuthal is equal to 3 times I. So that means every frame, it moves 3 degrees. That's pretty simple. And so in order to go a full 360 degree rotation, I need 120 frames. And I'm going to save it at 30 frames per second. And I'm going to call this Annie2. And of course there's an error, and that's because I need to change this as well. So subplot keyword argument, I need to make sure that it's actually 3D. So now make sure that it's a 3D plot. I can plot this, and it will save a second animation here. And so now you actually have the surface rotating, and so it's a lot easier to see from the past examples. So this would be one of the rare cases where I think it's appropriate to have a surface plot like this. Before I finish, one thing I should mention is suppose you have a nice plot like this, and you actually want to save it to your computer. Well, that's one final command, and that's plot.savefig. And I specify, for example, I want it as plot.png, and DPI is 200. So 200 I find is a good high resolution plot here. So if I rerun this, and it's back in the basic style of Matplotlib, that's fine. By the way, this is what it would look like in regular Matplotlib. You can see why I like the other one better. And I can actually open this, and I have a full resolution PNG plot, and you see that it looks really nice. Even the regular Matplotlib in this case looks decent. Anyways, I hope you enjoyed this tutorial. If you did, please like and subscribe, and I'll see you next time.